welcome to Numerical Ship and Offshore Hydrodynamics. Today is the lecture 58. Today we are going to discuss how we can incorporate some kind of nonlinear wave loads, for example green water, into the BEM solver. Now, for today's class I select that impulse response based method as a BEM solver, and there actually we can incorporate the green water loading. Now, the BEM solver you can take anything, you can take the time domain panel method also, no problem. But here for sake of simplicity we have taken the IRF based solution. Okay. Now, this is the keyword that you have to use to get this lecture. Now, let us start. Now, first let us try to figure out what is the slamming and green water just from this video. This video has been played before also. Now, again we have to see that when actually slamming occurs and when you have the green water load. Now, you can see here the bottom part of the ship actually hitting the water surface and hitting very badly, and that phenomena is called the slamming. Okay. Now, you can see that how dangerous this is, and it can damage the bottom part of the structure anytime. Now, let us see that what is the green water. Now, here also you can see that wave is coming and hitting to the deck, main deck. Now, here also you can see that it is also become, it is a very that is also very rough. In fact, this also sometimes leads to the structural damage of the ship. So, therefore, considering these two phenomena, slamming and green water, is really very important. Now, frankly speaking, both are not very easy to capture. Okay. However, you can see the importance from this video. So, it is very important, though it is very difficult to compute, still we need to at least give you some kind of idea or some approximations based on that, some formula we need to develop to figure out what is the slamming load and the green water load. Okay. Now, here let us try to model the green water load in very simplistic way. I will tell you that this the way I am showing it, it may not be that well to see the every details of the green water loading or the green water phenomena. For example, this method cannot capture that air trapping phenomena, like, or it does not capture the actual flow field, the plunging effect, everything. It is very, if you really study the green water in very deeply, that time you will come to know all these things. Now, here what actually, however, why it is important, because at least I could get that what would be the amplitude of the green water load, and which is essential to solve the ship motion problem or wave structure interaction problem. All I need to get that what is the response of the vessel, that what would be the magnitude of the green water. Okay. It may not be that how the water is actually flashing on the deck or how it flashes on the structure, superstructure of the ship. That is also important study. For that you have to do very rigorous CFD analysis. However, for this fluid structure interaction problem, we attack this problem, and only our botheration is what would be the magnitude of the green water load. Okay. Now, let us see how actually it is possible to do. Now, what we can assume here, there are lot of models are available. We are taking a very simplistic model. We can, so lots of methods are available. We are taking the very simplistic model here. We call the dam break model. Now, what we can see is, let us assume a column of water. Okay. And let us take the height of this column of water is z, and let us take the area of this this column of water may be some a. Okay. Now, if you use the Newton's second law of motion, so it says that force equal to rate of change of momentum. Now, here it is mass into the, so I am just writing in the bigger way, mass and multiply the relative velocity, or we can call the V relative. Okay. Now, how I get the mass, because this is a water column, right. So, definitely the mass, the expression for mass should be equal to the density of the water, and then the volume of the water, I mean this, it should be that multiplied by the area into the height, or okay, let us say not z, let us take the height is capital H. So, that would be the total mass. So, then I can write this equation again, this AF is equal to d dt of rho into A into the H, and also sorry multiply by the V relative, right. It's really easy. Now, pressure is nothing but a force per area. So, I can call this as the P dynamic. So, the dynamic pressure can be written as, now if I divided this by A, so it becomes d dt of rho into H into V relative, right. So, now here we can say that rho is coming out of this derivative. So, it becomes, you can call this dH by dt multiply by the V relative, and then rho into d dt of, or del t of V relative and multiplied by the H. Now, that I can think of this would be the my dynamic pressure. Now, my total pressure, so you can say this, the pressure total or P tot should be P dynamic plus P static. Now, what is the static pressure? The expression for the static pressure P static nothing but is rho into G into capital H, because from so this is what we are assuming, right. Now, physically what actually I am doing as follows. Now, suppose I am having, let us take a axis over here. Okay. Now, this pile of water actually I am releasing, and then I am allow it to break it here. So, that is something actually I am doing. So, it is a combination of static component and the dynamic component, and so therefore, if I replace the both, okay. So, if I replace the both, then I could get the expression for the total pressure, right. So, now so then the total pressure, that P total equal to, so I have to write d rho into del H del T into V relative plus rho into del T of V relative, and then into multiply by the H, of course, plus it is rho into G into H. Okay. So, I can take common here that rho. So, I can get into G plus del T of V relative multiplied by H plus rho into del S del T into V relative. So, this is the expression for the green water. So, this is how actually I can model the green water. This here this mathematics is not very complicated and direct, it is coming from the physics. So, derivation also easy. However, the derivation of slamming is not that easy. So, when we discuss the slamming, we can only go with the final formulations anyway. Now, this is fine. Now, even if we have this expression, it is not that easy to incorporate into the code. Now, here you can see that we have lot of parameter that we need to find out. For example, or we need to know the definition. For example, so this is a pile of water. A pile of water is there in the deck, and sometimes it is actually breaking it into the deck. It is fine. Now, how we can define these parameters, this for example, the h, and how we can define the parameter V relative, right. Now, let us see how we could do that. For that, actually we need to understand some basic ship geometry. Now, if you draw the profile view of a ship, okay, now we have, this is called the design waterline, and this part we call the draft T, and this is we call the freeboard, and then total it is we can call the depth, and this is called the main deck. So, this is the basic geometry of a vessel. Now, this we can, let us take, we can define the freeboard as small of FB. Okay. Now, this water, when green water is happening, now if this wave is coming, so if the height, if the height of the water is more than the height of the freeboard together with the height of the ship. That means, because here you have to understand that this ship is not in static position. Now, ship also is a dynamic position. So, therefore, this ship have vertical motion, we can call as a z of t, and also it has a pitching. So, it has, let us say you can call as a theta or z5, as when the way you know that. Okay. So, let us see that in our notation we call, let us say x3 and then x5t. So, this is hip and this is pitch. Okay. So, it means that vessel, let us take this mobile, like this vessel actually it is not still, it is moving, and it is moving with a in heaving as well as the pitching. So, in that way it is going. So, then I need to figure out when this green water phenomena will occur, and when and how we can compute this height h t. Now, clearly this height h t is nothing but if I take this amplitude, or you can say this eta t at that particular point, what is the wave elevation, and if I minus this with that ship displacement and plus the freeboard height. So, that would be the resultant height should be the height of the water column, right. So, we know, we understand this one. Now, thing is that how to get the ship displacement. Now we have to understand one thing, that we need to figure out that at which point I am interested to get the green water load. Now, suppose I fix a point here. Now, let us take the distance from CG to this point, let us say it is something xp. Okay. Okay, let me write in very bigger so you know this. So, xp. So, this is the distance between the point I am interested, where actually the green water can happen. Okay. So, the distance of that point to the from the CG is, let us say, xp. Now, thing is that this point xp also a variable point, right. For example, now this is my shape over here. So, this is the shape. Now, it can happen this green water normally, since the water is piling up and falling here. So, it can fall over here, 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 here. So, any point this can happen, but I mean in fact all point it might happen, maybe the intensity is different, the intensity it is splashing here at this point A, maybe when it is splashing at the point B the intensity is different, but however it is possible. So, it is run from A to B. Now, to again we are going with very simplistic way, let us approach to this problem. So, we are not taking the multiple point. Okay. So, here we are, let us take only a single point and we try to calculate what is the green water pressure or load is acting at that particular point, and then we can repeat the same phenomena for different point also. So, we can get a series of green water load along the length of the vessel. Okay. So, now let us take let me draw this again. Now, I just draw this the main deck, and now let us take this is my CG and this is the point I am interested. So, it is and then distance is let us say xp. Now, suppose it undergoes some kind of heaving and pitching. So, it means that let us say that it approaches to this point. So, this is the at any time, at any particular or instead of time t. So, now this is we can call this may be my the vertical displacement and we call the x 3. Okay, fair enough. So, now at some point, so it is this point, it is at at it is the z t at t equal to 0. So, this is the primary position of my, and with respect to this I am trying to calculate the whole thing. Now, at any point at t, so it moves from here to here. So, this displacement, this from here to here, this is, let us call it is my x 3 t. Okay. Now, it undergoes some trim also. Now, let us assume that bow down is positive. Okay. So, now if I draw this picture here little bit, this is my the point after actually I am pushing from z equal z t at t equal to 0, and it is from there is some t equal to t, it have this much of displacement. So, I can call it is at x 3 t, and here it has some kind of trim, or we can call it a positive trim. Now, if this is the point I am looking for, so this is my x p, and let us I am interested about this vertical point. Now, let us take this is my so this would be my final point. It first it is approaching here and then it has bow down. So, it down theta, let us say, or here we can, okay, let me go with theta only, because we have this notion. Now, I do not want to put this x 5 t here, it might confuse you. So, it has a theta, so bow down, and finally, this is my actually the relative position of the vessel. Okay. Now, how I can measure this point? It is very easy, from very basic trigonometry. I know my the sin theta, this equals to this distance, right. So, I can call this as let us take A and B, right. So, sin theta is nothing but A B divided by x p, right. So, therefore, this distance A B is equal to x p into sin theta, right. Now, here now with respect to this, if I now draw, then what is my the z, or I can call that, let us call z, it is because it is vertically. So, what is the z relative? Let us take this, definitely my x 3 t, which is the vertical shift, and then actually I down A B. So, it is minus into x p into sin theta. So, this is the displacement of the point. Now, this point it is a B point, let us say. So, this is the displacement of the point B at any time t. Now, if I assume that theta is small, if I assume my theta, of course, I assume this theta is small, because otherwise if I do not assume theta is small, I cannot write g over here, I have to write g cos theta, right. Because here also you can see here that it is a slanting. So, g, so it is the component of g is actually acting, which is g cos theta. Now, if so, this angle is theta, if this is theta, so this is theta, so it is g cos theta, but since theta is very small, so cos theta approaches to 1. So, that is why I write here g. So, when I write g, it means that I am assuming that theta to be small. Now, if theta is small, then sin theta equal to theta. So, finally, I can get the z relative is x p minus it is x 3 t minus x p into theta. Now, theta is nothing but my pitch motion. So, therefore, I can simply write x 3 t minus x p into x 5 t. Now, this is my z relative at any point of time t. Okay. So, this is nothing but my ship displacement, clear. So, therefore, that is how I get what is my displacement of the vessel, and that must be added to my the freeboard, right. Okay. So, therefore, now I understand that if I try to write that h t, so h t is nothing but my eta t minus it is x 3 t minus x 5 x p into x 5 t, and then plus this the freeboard. Now, I know what is the expression for eta, right. So, in fact, this eta is not, I mean, you have to find out the eta of that particular point, right. Now, again if I just draw the main deck, and now if this is the my point of interest, this point. So, at this particular point I need to know what is my eta t. So, I can write my eta t is nothing but this A cos k into that particular point, which is x p minus omega into t. So, here I just writing eta t at the point x p, right. So, that is how my relative velocity this displacement h t is eta t at point x p minus x 3 t minus x p into x 5 t plus your freeboard. So, now this is the h t I am getting, right. Now, if you remember the formulation that that the dam break model formulation. So, I know what is my h t. So, if you remember, I need to know what is the dH by d delta, that also I need to know, right. And this is nothing but my eta dash t at x p minus it is x 3 dot t minus it is x p into x 5 dot t. Now, there is no freeboard, right, because it is constant. So, if you differentiate with respect to t, it is going to be 0. So, now I know what is my h, I know what is my del h del t. Okay. So, now I need to know what is the other two parameter. Now, how to calculate the V relative and del t of V relative. Now, if you remember, I just see that this expression is nothing but your the relative displacement. Now, I just write the relative displacement at z t or z relative t, and this is nothing but my x 3 t minus x p into x 5 t. So, this is my relative displacement. So, therefore, my V relative this is nothing but x dot 3 t minus x p into x 5 dot t. Okay. And therefore, the last component that I need to know, that which is del del t of V relative, which is nothing but x double dot 3 t minus x p into x double dot 5 t. See, now you see you have this z relative, you have this V relative, you have this h, right, and you have this del h del t, all term you have. Now, only thing is that you substitute everything over here, you substitute all this value here at each time t, and then you will get the model the green water load at that particular point x p. Now, today we are going to stop here. So, in the next class I am going to show you that how I can use this green water load into the IRF based solution. Okay. So, till now, thank you.